Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to introduce Vishnu Datta, who's visiting us from the Microsoft Research India Lab. He did his PhD at Stony under Samir Das. And he's going to talk to us about spectrum sensing song Frontier. Vishnu.
Thanks, Dinan. Good morning, everybody. So today I'll talk about this platform called SpecNet. We've been working on this for maybe over 8 months now. This is work done with my colleagues at MSR India, Anand, Krishna, Ram and Venkat. And we also have a collaborator from Indian Institute of Science, Chandramurthy. So SpecNet broadly is about a platform which enables you to connect to remote spectrum analyzers, which could be anywhere in the world, lets you control it remotely, and you can build interesting applications on top of the platform, like distributed sensing applications. So I'll start with giving some motivation of why we started doing this. Recently, there have been a lot of studies which have looked at spectrum measurements, utilization of spectrum at different places. For example, some of these quotes here talk about spectrum underutilization in different parts of US. For example, the average occupancy in this band is around 5.2%, which is quite low. In Chicago and New York, again, it's slightly higher than the average, but it's still quite low. There's also a lot of recent papers which have also talked about spectrum usage in, say, China, Singapore, and other places. What all these studies have done is basically made a point or made a case that there is a need to open up this spectrum for secondary users, and that's what happened, right? So just to point out, this is how the spectrum usage looks like in India. It's mostly white. There's only one TV broadcaster in whole of India, and they are sitting on 200 megahertz wide spectrum, and they have like 2 or 3 channels. So it's pretty white in India.
And that's an average over time, presumably?
Yes. There is some dip here and there, but yeah, on an average, that's how. And as you all probably know, that sort of led to FCC in US opening up white spaces for secondary usage. I guess that's been happening even in UK right now. So one of the things that we noticed, at least in India and other emerging countries, is there's no such data for India or lots of other places, right? Most of the data is like for few of these countries like US and I guess UK too. And another thing is these spectrum utilization maps are mostly static snapshots at different times. If you want to look at how the spatiotemporal variation is over, say, 6 months, there's no such data out there existing for different parts of the world, right? And also researchers who want to do like white space research in terms of coming up with a new protocol, it would be very useful if such a data was available, because they could evaluate how their protocol is working with an existing usage map, right? So that sort of was the key motivation for SpecNet. What SpecNet does is basically it connects all the spectrum analyzers, which could be in different parts of the world, and exposes a certain interface to users who could be anywhere again, and they could basically task remote spectrum sensing jobs to any of these analyzers. We have basically provided a certain API interface for the users, and these API interfaces let you either control very finely what you want to do with the spectrum analyzer, or also exposes some higher level abstracts. For example, if I'm a policy expert, I mean, I don't want to go into the details of what's the resolution bandwidth is, what's the frequency span is or not. I mean, I just want to get a sense of whether a certain frequency spectrum is occupied or not. So we have certain higher level APIs for policy users as well. Other thing that the platform exposes is it also lets you develop distributed sensing applications in real time. So I'll talk about these applications as we go on. Now, at a high level, SpecNet allows three set of features. One, you can do simple remote spectrum measurements sitting anywhere in the world. Two, in the background, it's sort of offline tasking each of these spectrum analyzers which have been part of our platform to collect how the spatial temporal variation is. So it's sort of building this database in the background so that a user could just query the database and figure out how the variations were in the past. Thirdly, it also lets you write distributed sensing applications on top of it. So I'll go into details as we go on. So some of the challenges we faced with building this platform is spectrum analyzers are quite expensive, and there are not many out there, right? Few universities, some industries might have it. So you need to make sure that when you want to use this as a shared infrastructure, you need to make sure that the time is efficiently used. The spectrum analyzer's time is efficiently used. If there are multiple users who say submit a job of say sensing a certain region, you need to somehow come up with a way to efficiently schedule the tasks among the spectrum analyzers and complete the task as fast as possible. So yeah, managing the analyzers is a key challenge for us. So going ahead, I'll just briefly talk about the architecture of SpecNet, some of the components in SpecNet, and what programming interface do we expose for users to operate with SpecNet on. So this is how it typically looks. We have users who are volunteering their SpecNet spectrum analyzers to be part of SpecNet. What they need to do is basically install a client on a certain host, like it could be a desktop or a laptop, which is on the same network as spectrum analyzer. And the client basically connects to our SpecNet server, and a user who wants to perform remote measurements basically connects to the master server, and the master server is basically exposing APIs as a remote procedure call. So he just writes applications like this. He just writes a script where he pulls in the API interface of the server, and then he can call each of these APIs. And the server is responsible to figure out which particular slave server is going to run the task, right? Do interrupt me if you have any questions in between. In terms of the software architecture, this is the slave server. It's talking to the spectrum analyzer over a well-known protocol VISA, which most spectrum analyzers support. And we send SCPI commands, which is again a very standard interface that different spectrum analyzers support. So we are able to talk to different kinds of spectrum analyzers because they're not homogeneous, right? I mean, I could be having a TI spectrum analyzer and somebody else could be having another interface. In terms of the server side, we have API web interface through which the users basically send their API commands, and we have a scheduler which basically figures out how to schedule these tasks among different clients. And we also have the database, which is sort of continuously polling each spectrum analyzer and building the spatiotemporal map. in terms of the API interfaces, so we looked at what do the users want. So we sort of classified the users in these three categories. Sophisticated users are ones who sort of know exactly how a spectrum analyzer works, and they want to control each and every parameter of the spectrum analyzer. So we've exposed a lot of the SCPI interface to the users, and he can just write a simple script and run the task on any spectrum analyzer. And then there are these slightly higher API interfaces specifically targeted for policy users. You could basically say, get me the power spectral history within a certain region, and it's going to pull the information from the database and provide that information to the user. And finally, we've also come up with certain other API interfaces for, say, network operators. I mean, if I want to figure out whether there is a transmitter in this neighborhood, and if so, can I find out where he is? That's sort of something that a network operator would be interested in, because if I'm a TV operator and if some white space user is accessing the network, I would want to figure out who it is and where he is. And also, if I am a licensed user of a spectrum, I would want to know if there are other illegal users of the spectrum in this space. So these are sort of the APIs for doing that sort of an operation. So before I go into the details of SpecNet, let me give you some primer on spectrum analyzers, what they do and what are the things you can change in a spectrum analyzer, right? So typically a spectrum analyzer gives you a power spectral density of within a certain frequency band. So if I say from frequency f1 to frequency f2, give me the power spectral density, it's going to give you the power seen at different frequency bands, right? Now, there are two parameters that you need to give to a spectrum analyzer when you want to do a spectrum scan, right? One is the frequency span, which I talked about. I want to scan from f1 to f2, that's the span. And the second parameter is called a resolution bandwidth, that is, at what granularity am I going to scan this span of frequency span, right? If I give a very narrow resolution bandwidth, it's going to give me lot of samples within the same band. And if I give a larger band, you will have much fewer samples. Now, the frequency span and resolution bandwidth impact how the signal looks like when you are going to perform a scan. So let's just look at an illustration here. I'm just scanning certain band here, 700 megahertz. And this is the received signal power on the y-axis. And I'm going to show how the power spectral density looks like for different resolution bandwidths. So 1 megahertz all the way to 1 kilohertz. So when I do a 1 megahertz scan, in this particular scan, it's just showing me like a flat line, which is at say minus 45 dB. Now, as I reduce the resolution bandwidth, one thing you notice is the noise floor sort of drops down. The reason it drops down is because now my sampling granularity is much lower. So in those smaller granularities, I am accumulating a lot less noise. And I am able to actually clearly see the signal in this particular frequency. Right? Initially it just said this is how the signal looks like. Now when I reduce my resolution bandwidth, there are more features of the signal which are becoming visible. And if I go further down, I can sort of decipher the signal much better with a very low resolution bandwidth. And notice that the noise floor is also going down. Right? Now let's see what this has in terms of scan time, right? So, for example, a user wants to figure out how much of my spectrum is being used, right? Now, suppose this is how my signal profile looks like for 0 to 1 gigahertz. Now, if I were to put a threshold of say minus 80 dB as my noise floor, and say if there is any signal above my noise floor, I say that the signal, that particular band is occupied, right? Then for this particular noise floor, I say that these are the places where there is some occupancy, right? So you can see that the noise floor plays a role in figuring out which parts of the frequency are occupied and which parts are not. Noise floor also impacts how far I can detect a certain signal, right? So I have a transmitter here, and I have my spectrum analyzer here, which is at a distance d. Now the power of the transmission starts to decay usually at like a path loss exponent of say gamma here. So it's sort of exponentially decaying. Now if I were to detect this transmission, it has to be say a certain threshold above the noise floor at the spectrum analyzer, right? So I would need to set my resolution bandwidth high enough or low enough so that the power received at the spectrum analyzer, it should be above a certain threshold above the noise floor. That's the intuition behind setting the resolution bandwidth. So let me talk to you about some of the challenges in doing this scanning operation, given that you have say few spectrum analyzers within a certain region. If I have multiple spectrum analyzers, I would have to figure out how to share the scan operation among these analyzers. To do that, let me talk about the scan time versus the frequency span. So here's a graph of frequency span along x-axis and the time to scan the frequency along y-axis. And I have data for two different analyzers here, analyzer 1 and analyzer 2, and for two different resolution bandwidths. The first thing you notice is as the frequency span is increasing, the time to scan starts to linearly increase for any particular analyzer. The second thing is across analyzers, time to scan for the same frequency span could be different, right? So given the heterogeneity of different spectrum analyzers out there, I sort of need to figure out how long does a spectrum analyzer take to scan say certain frequency span. So I need to sort of build this map offline for each spectrum analyzer which is part of my SpecNet. Second thing you notice is by reducing the resolution bandwidth, the time to scan actually increases non-linearly in terms of 1 kilohertz and 3 kilohertz. So it takes more time to scan if I go from 3 kilohertz to 1 kilohertz. So that's the non-linear impact. The time to scan is sort of inversely proportional to the resolution bandwidth. So here I have resolution bandwidth along x-axis and the time to scan, and you can see that this is more in log scale. As I change my resolution bandwidth, the time to scan is sort of exponentially going down. So given these properties of impact of resolution bandwidth and detection range, how do we now do spectrum scanning? So the problem is, now a user is interested in scanning a certain region and there are multiple analyzers in that region. Now how do you schedule a scan operation? Now one thing I could do is I could split my frequency span into say two halves, and S1 could scan the first half and S2 could scan the second half in order to reduce the total time of scan. Now since each analyzer has a different time to scan for the same frequency span, I would need to sort of divide my frequency span in a proportional sense. How fast does a spectrum analyzer scan a certain frequency, and using that I sort of divide my scan time across the two spectrum analyzers. And another approach I could do is sort of do it in a geographic sense, right? So instead of dividing the frequency span into two chunks, I let both the spectrum analyzers scan the entire frequency, but for a much shorter range. What I mean is, suppose I divide this entire region into two halves, and I let one of the spectrum analyzer only detect within this range and the other spectrum analyzer detect in the other range. What happens is, for each analyzer, the detection range is much shorter. As a result, I can set a much higher resolution bandwidth, and as a result, I'm going to get a much faster scan time, right? So what we have a certain algorithm which basically figures out how to partition it based on this Voronoi approximation partitioning, and we figure out exactly what should be the range for each spectrum analyzer. And then we also have a hybrid approach, which is sort of a geospectral sharing. For example, I could do partitioning in frequency space as well as the spectral space, the spatio-temporal space, right? Now, in terms of performance results, so here's certain. This is the IISc campus, and we had a few spectrum analyzers deployed in these three locations, and the region of interest was this circle where I wanted to do the spectrum scanning, and these are the numbers for time to complete the task for these three algorithms that I just mentioned. As you can see, the hybrid approach is the most optimal one, which is able to complete it in much faster time compared to the other two schemes. So let me quickly go over to the website. So this is the website interface for SpecNet. These are the APIs that our SpecNet server exposes. So there are some examples which I can run directly on the website. So a remote user could write a simple script and basically call those APIs that I talked about, right? So let me show you some of the examples. So if I want to just do a simple scan, what I'm doing here is just calling get power spectral density, and I'm specifying the resolution bandwidth and the span, right? So what's now happening is I'm just sending this query to the analyzer, and I immediately got the data. So this is the data from one of the nodes which is running in Bangalore right now. So this is how the data looks like right now in Bangalore. I could do a lot more interesting stuff, like for example, if I want to find out which is the strongest FM tower in my neighborhood, I can basically do some more operations on this and zoom into the region where I have the strongest FM transmitter. So what I did basically was initially I made a single call and figured out which is the strongest FM signal, and then I'm zooming it by reducing my resolution bandwidth, and then looking at how the signal profile looks like for a certain transmitter, right? But a bunch of spectrum analyzers, and we wanted to localize a microphone. And these are the actual and the estimated one are shown here. So coming to the limitations of this platform, one of the things we are finding it difficult is to find volunteers to join the SpecNet. So I mean, me and my colleagues are going around talking to people who have spectrum analyzers, talking to universities, and trying to get them into the platform. And one of the issues is that these analyzers are sort of located within certain buildings where there's a lot of attenuation because of the building walls and whatnot, right? So when you're scanning, you're already taking a 20 or 10 to 20 dB attenuation, so the detection range would be much lower for each spectrum analyzer. And also, like when we talked to a few of these universities, one of the things that came about was now that I can actually finally control the spectrum analyzer, will I be able to actually decipher what data is being transferred, right? I mean, they don't want these spectrum analyzers to sort of act as sniffers and figure out what's happening around. Most analyzers don't let you get the data. It's mostly the spectrum analyzer just gives you a power spectral density, which is from which you cannot actually decipher the data. But there are some analyzers which can actually expose much more information. But we sort of limit the API interface so that that doesn't happen. So in conclusion, I mean, we right now have this platform up and running, and we have few nodes. I would encourage whoever has a spectrum analyzer to sort of take a look at it, and also, and the thing is, there's already enough data out there, so they can start using the data to see how the spatial temporal variation is happening. One other thing that we are also looking at right now is the cell phone bands. Because cell phone operators want to know how the coverage is at different parts of the town, right? So you could use this same platform to also look at cell phone data coverage, right? That's another thing that we're looking at. That's about it. Yeah.
I presume then that there is no antenna. You just leave the spectrum analyzer where it is.
You definitely need an antenna. The antennas are typically in the 0 to 1 gigahertz range. If without the antenna, your noise floor will be.
You're not assuming a rooftop antenna.
No. So the one that I just showed you is a spectrum analyzer which is inside the building with an antenna connected.
Just inside building on top of the spectrum analyzer. So it's not as
no, it's not outside.
An antenna on top of the roof with a.
No. The antenna is disconnected right there. But if the antenna is outside, then your detection range would be much larger. Yeah.
I'm curious how you see the trade-offs between the kind of model you've described here, where the system is very much an online system where you submit jobs to do the sensing, versus a slightly decoupled system where you permanently run them in a fairly standard configuration and log all the data to a database, and the jobs come in to query that data. Did you consider both those designs? What do you see as the pros and cons of those?
I mean, you basically limit the kind of applications possible if you were to do just offline, right? So the things like detecting a transmitter and localizing it might not have happened because there are some runtime decisions that you make based on what you saw, right? You could change your resolution bandwidth and then did another scan. But if you were to do just offline, I mean, you would do it for a standard configuration, which might not let you.
Right.
So the offline thing was more for providing a rich data set for researchers and also the
that sounds
policymakers.
really useful, right? I mean,
Yeah.
that kind of data.
And the other thing was we looked at sources of transmitter locations, right? For example, in US, they have a database which says where are all the cell phone towers and TV broadcasters are, right? In emerging markets, like for example, in India, there's no such database that's out there. We did go and talk to the actual TV transmitters and we asked them for data, and those data was highly noisy. So this sort of was a clear way to get all the TV transmitters out there. And once you have that data, you can actually go to the government and say that it's underutilized. Because if you just go and say with one scan in Bangalore that it's highly underutilized, that they're not going to believe you.
So I think follow-up question also is I was trying to gauge from this where the offline sort of interface to this was, because clearly that is really useful for policy agencies and people might want to know what's going on right now. Not right now, what's going on last week.
Yeah.
Being part of SpecNet, if you add an analyzer to this, is there some kind of background task that's just generally scanning around? If there's no online jobs, will it just naturally just
Yes.
to airways?
Yes. So the user typically can reserve the time when he is actually using it, right? For the rest of the time, it's sort of utilized for SpecNet. And during that time, if there are no user requests coming in, the master server sort of periodically runs a scan job so that it gets a spectrum scan and it's being pushed into the database so that later on I can do query sort of a thing that you asked, right? So I could figure out how the spectrum usage was, say 10 days before, and how is it now. But I might not be able to do a lot of things with that because I'm doing it for a standard configuration, like 10 kilohertz resolution bandwidth, the entire span, which typically takes around at least 10 minutes to scan the entire frequency span.
On that subject of trying to build this sort of nationwide map, clearly these are expensive bits of equipment, so the number of spectrum analyzers that you'll have dotted around the country is probably quite low. Have you thought of ways that you could increase that, either by maybe building very cheap, not so high quality, just to get a broad sense of roughly what's going on?
So we've done two things. One in the line you talked about. So we've been looking at trying to get a low-cost spectrum analyzer. At least for India, what we are trying to do is get a bunch of these analyzers and give it to universities. And we'll have fixed deployment, and we'll be running our jobs and sort of bootstrapping SpecNet. The lowest we sort of found was around 2,500 USDs. 2,000, yeah, that's the range. But I'm guessing that there should be, if you want to build an analyzer, you could do it at much lower cost. But I guess there's no requirement for somebody to build a low-cost spectrum analyzer. I don't know if that's
so there used to be this company that used to produce what was called Wi-Fi Spy, which was spectrum analyzer, but for the Wi-Fi.
Wi-Fi, but we could not find anything for because this is a much larger.
Yes, correct. What would be the costs, right? If you take that design, that idea, and move it forward for the ranges that you care about, how much do you expect that it will increase cost? Is it?
So some of these spectrum analyzers have a lot of fancy stuff which we do not need.
Exactly.
So I'm guessing a lot of the cost is going into that portion. So I don't know the numbers, but maybe under $1,000 should be feasible. That said, so the other thing that we are trying to look at is having mobile spectrum analyzers. So one thing we've done is we also have a client which runs on a mobile. It's a mobile client, so it takes in data from the GPS location, right? If you have a GPS device and the client, it can basically do a scan and find out at what location the scan was, right? So that can sort of give you a lot more information, but it's sort of limited in the sense that you need somebody who's driving around, or you need to have it deployed in some sort of a public transport or something, where it's sort of continuously going around in the city so that you get a wide coverage.
And you presumably also need to have some kind of analyzer connected to the phone, or are you just thinking of the Wi-Fi bands here?
So right now, at least, the data that you're getting is actually not that much. So one scan would typically be around 30 kilobytes.
But you need to have a scanner connected to the phone.
Yeah, so you could basically compress it and send it across. So you would definitely need a backhaul, like a cellular backhaul.
So I was just wondering about your technique for combining the measurements from multiple spectrum analyzers to get an idea of the power density in a region. Did you have to build in a lot of GIS information to that, or did you just assume fairly sort of straightforward line-of-sight propagation? Because also there could be multi-part, there could be part of that makes what you sense a bit sort of hard to combine.
So what you're pointing is what is the model of the propagation model that we assume here. And right now there's a standard default setting of say 3 for indoors and 2.5 for outdoor propagation. But that said, yeah, the gamma. And that said, it's a parameter in the API where if a user has some offline information of how the terrain looks like, he can actually feed in the right gamma, and he can do things like localize the transmitter much better.
I guess there's things like standing waves as well. Can sometimes interfere
if you
your
move
antenna in the wrong position, depending on frequency.
Localization is something that it gives you like a rough granularity. For example, we tried to localize the TV tower, and we were within like some 500-600 meters. So this is not like few meter error. It's quite a lot, but that's good enough for a TV transmitter kind of a setting where the range of a TV transmitter is like tens of kilometers.
What do you do about, I noticed on one of your previous slides you were talking about splitting an area into two.
Yeah.
Haven't you seen any issues with being able to detect very low power users of that spectrum, even if it's quite local? So if you're trying to split up that area into two chunks and then you're raising your resolution bandwidth,
yes,
that effectively ups the noise floor.
Yes.
Okay, so if you're then trying to detect sort of low power users rather than TV masts and things, aren't you seeing those users go below the noise floor and hence kind of invalidating that scan?
So the way we do it is we take into account the noise floor. So when I split the region, right, yeah, so in the previous case, the farthest distance, so typically a user gives a center of a region and the radius of interest, right? So this is the region where I need to detect, and I know the locations of the spectrum analyzers. So for this spectrum analyzer, the farthest distance that it needs to detect is this much, right? And the user also gives me what is the threshold above the noise floor that I can do when I say that there is a transmission, right? Now, given these two parameters, I know what is the resolution bandwidth I need to set for each spectrum analyzer. Now, in the second case, what we did was we split it into two. halves, and then I know what is the resolution bandwidth I need to set so that I can reliably detect the transmitter given the parameters of the threshold, right?
Okay.
Any more questions? No? Well, thanks, Steve. Okay.